All right, everyone. So today's lecture hopefully is going to be quick. I'm trying to make it quick, but we're going to start with that you should never do a median split. Now, here's a demonstration. Now, those of you that don't know what a median split is, it's when you have a continuous independent variable, you find the median, and you make it dichotomous or categorical. So, like, a lot of folks have introversion and extroversion as an independent variable. So what they do is they're finding, like, the median of that specific data set, and then they're splitting people into low and high groups, saying that, oh, they're low and high on introversion and extroversion. Now, what does that mean? Let's see a demonstration of why this is real bad, okay? This is real bad, all right? So these are self-esteem scores. I'm not even putting it in a design, and you'll see how bad it is. So we got a 0, 0, 0. These people are struggling, right? 1, struggling. 2, struggling. 3, not so struggling, but not so good. 4, not so struggling, not so good, getting better, right? Having okay self-esteem, right? Versus all these 5s. This is an analysis you would see in an American sample. All these self-esteem scores way up here, right? So our median, the way I set it up, falls right at 4. So everything on the left of that 4 is low and everything to the right is high. That's just how a median works. So you say the median was 4.5, so 4 is low, 5 is high. And so now what we're saying is that this 0 is the same value as this 4, right? We're literally saying they have the same self-esteem, and that is complete and utter false. You can't do that. This is bad. Like, our goal as scientists is to remove error from our data. This is horrible. You don't do this. You don't add error to your data. You do it. I get that you did it, but you did it because you didn't know a better method. And Stats Dork is going to teach you a better method. But, you know, when you look at this, that 0 is not the same as the 4. What do we do instead? It's called multiple regression, and this will be the first class you take in grad school if you're getting a PhD in psychology. It'll be called statistics, but they will teach you linear models, okay? But it's called multiple regression, and in order to understand it, which we're only covering the surface, so if you want to understand it more, you can come to my office and we can talk more. You might challenge me to figure it out better to teach it. But essentially, in order to understand this, we need to understand high school math. All right, so I just want to start off today's discussion with a high school algebra review, because this algebra review is the foundation of multiple regression, the thing I'm trying to teach you today. So it's the conceptual foundation of what's going on. Now, I remember being in algebra 1 and 2, and I'd get an equation, like an equation of a line like this: y equals mx plus b. It's something you've heard before. Y, your output, equals some slope times some input value plus some constant. So you have two variables. You know, you have a y variable and an x variable. You're predicting the y from the x. And often you were given an equation like y equals negative 0.5x plus 20. And what you were asked to do was draw the line out. So I'm actually on the right. I'm drawing out what my high school answer would have been. And I'm like, when x equals 1, y equals 19.5. When x equals 10, y equals 15. And I got that by simply solving that equation. I plugged 10 in there. That's negative 5, and that equals 15. Negative 0.5 times 10, right, is negative 5. And that is... plus 20 is 15, right? No big deal. That's where that's coming from. When x equals 50, and I put 50 in there, right? You got 0.5 times 50 is what? Well, that's negative 25, right? Plus 20 is negative 5. So then I just draw my line out, and I was fine, right? You all know this. Y equals mx plus b. So what we're doing in multiple regression is, we're not drawing the line like this. What we do is we insert our y and our x. So we insert a column of dependent variable scores and a column of independent variable scores. And what we do is we allow computers to fit a line of best fit. And then from that line, we get our slope, our m. The what we're doing is allowing a computer to tell us what our slope is and allowing us to know if that slope is significantly different from zero. The null hypothesis in this test is that the slope, these betas are zeros. So, or that these slopes, these m's, I'll call them beta in a second, are zero. But that's essentially all you are doing. That's essentially all you're doing with multiple regression. So with multiple regression, we need to understand our line equation first. Y equals mx plus b, it just got more complicated. So you can see the same structure. Y equals a slope of some x plus a slope of another x plus a slope of the interaction of those two x's plus the intercept, right? So you can see that general setup, but when we're thinking about linear models in stats, it's just best to think what are the factors that are predicting our dependent variable. So our dependent variable is predicted by an independent variable and another independent variable and the interaction of those two independent variables and some slope value. So what we're going to do is we're going to enter in a column for our dependent variable. Well, not a column, like a set of data for our independent variable, a set of data for our dependent variable, set of data for our independent variable 1, a set of data for our independent variable 2, and then we're going to have then the computer is going to create a third column that's the multiplication of independent variable 1 times independent variable 2 plus some leftover garbagey value called the intercept. When everything's 0, the intercept equals, we don't know, that's the intercept. So essentially we plug in that data and then our computer estimates the beta of independent variable 1, the beta of independent variable 2, and the beta of the interaction. So, and it also does the beta of the slope, but nobody cares about that. And then what multiple regression does is test those betas against a null hypothesis that their true value is 0, and they look at a measure of standard variation around that beta estimate, which I'm not going to talk about too much just because it's pretty complicated and I want you to be able to do the analysis, but not necessarily, I'm not giving you the knowledge to teach it today. I'm just giving you the knowledge to do it. So essentially these beta values are correlation coefficients interpreted the very same way. And I think that's really important. Now, they are they're purified. Now, what that means is when I'm looking at independent variable 1, and I'm looking at its effect on the dependent variable, all the shared relationship between independent variable 1 and independent variable 2 is completely removed. The same goes for independent variable 2. All the shared relation, like if we're looking at the effect of independent variable 2 on the dependent variable, any shared relationship between IV1 and IV2 is removed. So none of that shared relationship actually exists. It's taken out. We're looking at purified predictors here. And that's true for the interaction as well. The interaction is purified for the main effect 1 and main effect 2. Okay? But I want you to see that. Like these aren't just raw regression or correlation coefficients. These are purified or controlled for correlation coefficients. So now imagine, you have a situation where you have a tradition, and I'll show you how to do it, but you have a traditional ANOVA framework, but you want to control for family SES or socioeconomic status. Well, you can do that in the regression framework, and I'll show you how to do that in a second. But if I want to look at the effect of wealth on happiness, controlling for like personality variables, right? I could easily do that with the multiple regression framework because when I enter in 2 predictors, the analysis works by purifying predictor 1 from predictor 2 and predictor 2 from predictor 1, and the interaction's purified from both of those predictors. So it's all just frankly purified. So correlation coefficients, we didn't talk about in class, but I want to tell you right now, when you have only one predictor in a regression, you only have one independent variable and one dependent variable. The beta the predicted line of best fit is your correlation coefficient, okay? So when you only have one predictor, that beta in your regression is your correlation coefficient. That line of best fit is your correlation coefficient, okay? And one of the things that is important to understand is that correlation coefficients are effect sizes by their very nature when you square them. All that stuff with partial eta squared, all that is a correlation coefficient, and then we square it. So right here, we have that our correlation value is 0.5. We square it, and we find 0.25, and that means 25% of the variation in our dependent variable is associated with variation in our independent variable. So it's that same predictor style. I'm not going to go through all of these, right? But in terms of correlation coefficients, a correlation of 0.5 is considered a very, very large correlation. And a correlation of 0.3 is considered medium, and really anything in the 0.2, 0.1 range is considered pretty damn small. So it's really like, is your correlation large? Is your correlation 0.5? Is your correlation medium? Is it 0.3? Does it count for at least 9%? Right? If your correlation coefficient isn't accounting for at least 9% of the relationship between the independent variable and the dependent variable, and like you have a significant correlation, who cares? It's tiny. So really anything less than 0.3 is bad. Anything greater than 0.5 is massive. And you can see why. It's like an exponential relationship, right? You see that like 0.3 is 9 and 0.5 is 25%. So it goes from like less than 10% to a quarter of the variation. But essentially, essentially, like, if you have a negative correlation, you square it, it's still the same. You interpret it the same way. But ultimately, when you're doing multiple regression, you're just getting a bunch of purified special regression coefficients. But that's really it. That's all you have. So I also think it's really important that you understand that the ANOVA framework, the ANOVA that you've run, is just a special case of multiple regression. In fact, you can replicate any ANOVA analysis that you've run with a multiple regression. And I'm just saying this because I need you to realize that your ANOVA is just multiple regression. I need you to understand that underneath the engine, what's going on, like when you put that stuff in that multivariate part of SPSS, that multivariate part is a little bit of a clue that you are using multiple regression. That univariate part, that's a cute clue as well. ANOVA is where you do all the stuff I showed you how to do with the sum squares and all that. That's like geometry. Well, with the linear model, that's like calculus, but they have the same answer. They're just two different ways to look at it. So when you look at ANOVA, you're looking at sum squares total and sum squares the effect and sum squares error. You are doing a different method, the geometrical method, right? But there's also this linear calculus method right here that allows you to get the same exact answers and responses. Those of you that have to take physics know you got the trig-based and the calc-based, and they're different. Well, it's a very similar type of distinction here. But I need you to know that ANOVA and regression are the same exact, give you the same exact result. Okay? And based on that, then we can go on and modify that linear model, the calculus form, to examine not only categorical predictors, but also continuous ones, and a mix of both. So if you are planning on going to graduate school, the top programs have shifted over from teaching folks ANOVA and t-test first to teaching multiple regression and linear models, because they've found that the linear models are more flexible. You can do more with them. You can have more complicated data analysis structure. So if you're going to get a PhD from a major psychology university, what you're going to notice is that the first thing they teach you is multiple regression. They're going to teach you ANOVA and a multiple regression type framework, and you're going to learn how to do that. They're likely going to teach you the stats program R that I'm using as well. So I think that's just important to know that this specific analysis that I'm only spending 1 day on is the foundation of the next frontier, right? It's what you should be doing next. Now, let's just put your research methods project into a multiple regression framework. Your dependent variable equals the beta of your independent variable 1 plus the beta of your independent variable 2 plus the beta of your interaction. So beta of your independent variable 1 is just your main effect of independent variable 1 expressed as a correlation. Your beta of independent variable 2 is your main effect of independent variable 2 expressed as a correlation instead of an F stat. Your beta of your interaction is just an interaction expressed as a correlation, right? Instead of an F stat. So all right, I don't want you to memorize this, but I'm using this for you to understand when I say ANOVA and regression are the same thing. Your F equals, you need to understand two formulas. Remember when I said that a t-test squared is just an F statistic? Well, F equals t squared. And then R squared, right, the R squared value, right, equals t squared divided by t squared plus degrees of freedom. Ultimately, I don't want you to memorize these. I just want you to see that you can find R from F. You can find F from R. They're interchangeable. So this is just more proof that what I was saying earlier is true, that ANOVA is just a special case of regression. That's it. So now that we've entered the end of this section, right, we should understand that we can still run an ANOVA with multiple regression. It is preferable to choose the ANOVA steps over the regression steps, just because it's a little weird in terms of interpretation, and you'll see that when as I'm working through the problems today. But if you have completely categorical independent variables, then run your ANOVAs just like we have. But you know, you have the ability to examine the ANOVA so much more with multiple regression. And also you need to understand that, frankly, ANOVA was just discovered first, and it was that geometric way that I showed you in that artistic sum of squares analysis. That geometric artistic way was discovered first, and then we figured out that this calculus way is identical. And that's often how things work. But I need you to realize that this sums of squares way and this linear model, linear equation way are identical. All right, so let's just work on a very simple problem together. We have 3 continuous predictors, and this is the case that multiple regression shines, when you have a completely correlational study where you just measured things. But it's still a beautiful design, okay? Like, I know you're like, correlation is not causation. No, it's not. But with these correlations, you can do work that, like, real-world analyses. You can look at so much more. You can find the same types of effects and make the same types of conclusions that you can with an ANOVA analysis. The only thing you can't say is cause. So if you have 3 continuous predictors, if you just measured 3 things at the same time, you can do an analysis that's as complex as your 2x2 ANOVA. So in this case, I'm going to show you in a second how to do this with my program. But you have a continuous predictor of happiness, or the outcome is happiness. You're trying to predict that from wealth and love and the interaction of wealth and love. Wealth is just a self-reported wealth scale. Love is just a self-reported how much love they're currently in scale. So we're going to throw these numbers into our program and see what. All righty. So if you go to the very bottom of our stats program, what you will find is you will find this multiple regression final frontier. You should use that for when you are trying to do a multiple regression with all continuous predictors. And we're just going to wait for my stats program to load. Hopefully we get lucky. All right. So now we're at the top. I'm moving all the way down to the bottom. We have 3 continuous predictors in this example. We have happiness being predicted from love and wealth. Okay? And that's directly taken from our previous PowerPoint slide. What you have to do, if you just want to do 2 predictors, you just enter in your dependent variable, your outcome that's more important than the other outcomes. You're like, which one's that? For me, as a researcher of race, that's always the racism measure. For you, it's the thing you want to change. For a clinician, it's always going to be like depression scores or happiness. It's the outcome that's most important, right? For somebody that studies academic performance, it's always grades. For somebody that studies kids, it might be how quickly they solve a theory of mind problem. For cognitive psychologists, the dependent variable might be how well they read, right? Their actual reading scores. It just depends on your outcome of most important interest. Then independent variable 1, independent variable 2, they're just your 2 predictors. In this case, love and wealth, right? Are they in love? Higher numbers indicate yes, lower numbers indicate no. How much wealth do they have on the scale of wealth? We put these in and we predict them. And so then if you wanted to expand this, you could add another independent variable here. Here, this is just the crappy thing you have to do. So you do scale right here. What that does is it converts everything to standardized scores so that you get betas. Okay, you get those correlation coefficients. If you don't do this step, you're not getting those correlation coefficients. And then we do this. This step right here is just a weird nonsense step that we had to do to work with the program. So if you add another independent variable, you have to add scale of IV3. You have to add IV3 equals C IV3. And then you have to say my data equals data frame DV IV1 IV2 comma IV3. So here, though, is the place where you specify the linear model you want to test. So I want to look at that true full like 2x2 kind of ANOVA model where I got a main effective independent variable 1, a main effective independent variable 2, and an interaction of independent variable 1 and 2. If you added independent variable 3, you would actually have plus independent variable 3 plus IV1 colon IV2 plus IV1 colon IV3 plus IV2 colon IV3 plus IV1 colon IV2 colon IV3 to get a 3-way interaction. I'm not going to make you do that. I'm just letting you know how to do that. And then that's all you have to do, but you can look underneath here. There are some things, particularly there are places where where graphs are made down here that you might want to alter, that you might have to add another one, right? Like if you add another predictor, you would really have to kind of like, yeah, don't worry about it. But I'm just saying this is the foundation of everything. So I really commented out this code so you could figure out how to expand it to other cases of other predictors. But also this is the point in the class where you should start feeling a little bit more comfortable Googling questions, a little bit more comfortable getting out there and learning how to do a new analysis from somebody that's not me. It's not going to be perfectly easy, but part of what I do every day when I'm doing this is just like, oh, what's the best analysis? Has anything new come out since the last time I've run this analysis? And so, I'm just trying to figure out what's the best way to do this. And what's really cool is that there have been advances in the last 10 years that have changed the way I analyze data. But essentially what you have to do is enter in your dependent variable, your independent variable 1, your independent variable 2. If that's all you got, which that's all you're going to have for homework, you just click run. And what you'll see is don't worry about that. You see a basic regression predictor table. You have your betas, which are just those special correlation coefficients. If you square them, you learn about the percentage of relationship between your variables. And you'll see that we have a couple predictors that have quite strong relationships. This 0.55 is over 25% of the variability in the dependent variables predicted by independent variable 2. Independent variable 1 over 6, we have 16% of the variation in the dependent variable is predicted by independent variable 1, right? This standard error, this t-score, they're all related. Beta divided by standard error equals t. Beta divided by standard error equals t. Our p-values are here. These are non-significant predictors. Our interaction is also a non-significant predictor. It doesn't matter that the t is negative. None of that really matters. But this is your main effect of independent variable 1, main effect of independent variable 2, and the interaction of independent variable 1 and 2. It's just multiple regression, and all our predictors are continuous. So then what we have here is we have our interaction graph, and I want to show you something. Like I've said, there's 2 ways to break an interaction. And if you notice, I just changed the order of independent variable 1 and independent variable 2. In the first one I ran, you can see that I have different lines, okay, for when independent variable 1 is low and high. And that's because here I had lines was independent variable 1. So you can break up your graph and you have different lines for independent variable 1 or independent variable 2. Now, independent variable 1 was love and independent variable 2 was wealth. And we don't have different groups. So how do they do these different lines? Well, what they do is they say, okay, what happens when we set independent variable 1 to 1 standard deviation below the mean or 1 standard deviation above the mean? What predicted values do we get when independent variable 2 is also set to be 1 standard deviation below the mean and 1 standard deviation above the mean? So when independent variable 1, love in this case, is set to be 1 standard deviation below the mean on love, but 1 standard deviation below the mean on wealth, their happiness score is here. When they are 1 standard deviation above the mean on wealth, their happiness score is here. And these are massive variability bars. You can see the error bars there. They're actually covering up the green ones that are behind it. But essentially, we enter these values. We find out what 1 standard deviation below the mean and 1 standard deviation above the mean is on each of our independent variables. And then all we do is we plug them into our equation. Now, I know you're not seeing it, but like what we have here is we have a dependent variable equals beta, right? Equals the beta of the independent variable times the actual value of the independent variable, plus the beta of the other independent variable times the actual value of that independent variable, plus the beta of the interaction term times the value of independent variable 1 times the value of independent variable 2. Now, you're like, wait, where are all these values coming from? We just look in our data set and we set independent variable 1 to 1 standard deviation below the mean. We figure out what that value is. And then we also figure out what one standard deviation above the mean is for independent variable 1. And every place in the equation that we see independent variable 1, we plug that into our equation. In fact, I'm just going to go ahead and pull up a notepad here. New note, get a new note. Let's go ahead and go back here. I want to make it small, right? And I want to just solve the equation for you, right? So our dependent variable, which is happiness equals our intercept, 0.16, plus 0.40 times independent variable 1, plus 0.55 times independent variable 2, plus negative 0.23 times independent variable 1 times independent variable 2. And so what I was saying before is like imagine if 1 standard deviation on independent variable 1 equaled -5 and so that's 1 standard deviation below, 1 standard deviation above on independent variable 2. Let's just say that equals +5. Say 1 standard deviation below on IV2 equals -1, and 1 standard deviation above on IV2 equals positive 1. And in fact, because all of these values are standardized, I forgot about this till just now. So because I use that scale transformation on the data, 1 standard deviation above the mean on standard deviation on independent variable 1 is positive 1. 1 below is negative 1. So if we want to get our predicted values of happiness, right, we'll just do 0.16 plus 0.40 times 1, right, times 1 for 1 standard deviation above the mean plus 0.55 times 1 plus negative 0.23 times 1 times 1. I just took my values from here and plugged them in to the equation. So when we're doing that, what's our predicted value of happiness? Happiness equals 0.16 plus 0.40 plus 0.55 minus 0.23. And then we'll just do our math. Happiness equals 0.55 plus, because I just added those two together, plus 0.55 minus 0.23. So that's going to equal 1.10 minus 0.23, right? So then what we're going to end up with .87, I believe. If I did my math right, that should work out. Let's double check. 7 and 3 is 0. Carry the 1. 8, 9, 10, 11. Perfect. So that does work for when we are both 1 standard deviation above the mean on both values. Let's just make sure that this looks like it makes sense. When we are plus 1 standard deviation on both values, while our graph, our picture isn't the best, plus 1 and plus 1, we can see that we are, this is 1, so we're a little bit under 1. That looks like it's about 0.9, 0.87. So it looks like we're right where we should be. Those predicted values are right where they should be. We do that 3 more times for all the other points. That's how we get those simple slope values. Okay? That's where all this stuff came from. And that allows us to understand the nature of the interaction. Right? Totally. It does. And so then we basically have everything that we need, except that there's something called a simple slopes test. And if you look here, I want to know if this green slope is significantly different from this orange slope. I know it's not because we do not have a significant interaction, but simple slopes test would allow me to see what the slopes are. Are they different from each other? And so when independent variable 1 is at 1 standard deviation below the mean, and independent variable 1 is at 1 standard deviation above the mean, are these two slopes different from each other? And so what we have to do here is we got independent variable 1 is 1 standard deviation below the mean. This slope estimate, they're saying, is positive at 1 standard deviation above is 0.31. So at 1 standard deviation above, we got a positive slope, but it's not as large. Has the positive slope here where independent variable 1 is negative 1 of 0.78. So it's like you can see these slopes are pretty different, actually. And right now we know that these two slopes, this one's 0.31 and this slope is 0.78. When we do a test on it to compare if that slope is different than 0, we find nope and nope. Okay? And I've always said there's 2 ways to break up your data. And what that means is you can have the different lines for independent variable 1, or you can have different lines for independent variable 2. So all I have to do here is just make sure my line variable here are correct. So right now, right, I have independent variable 1 as different lines by, so I want to do independent variable 1 as my x's and independent variable 2 as my lines by. And we're going to go ahead and run that. And then what you're going to see is that we get different lines. Right? So you see how it was independent variable 1 up here. Now it's independent variable 2. So this is what the independent variable 2 lines look like. So now if I want to understand these simple slopes, this slope for when independent variable 2 is -1 is 0.63. So we can see that. That's a pretty positive slope. And when it's +1, it's 0.16, which is basically a flat line. That's exactly what we're seeing. Is this slope significantly different from 0? Nope. Is this slope significantly different from 0? Nope. Right? So then, that's just it. If you have a significant interaction, you'd follow it up with these simple slopes tests and these simple slopes pictures. But ultimately, you just need these beta predictors and this p-value. I'm not doing confidence intervals today just because this is complicated enough. I don't want to add something even more complicated. But that's it. That's how you do this analysis. They tell us. When should you use multiple regression? When at least one of your independent variables is continuous. You can use it. You need to use it if you have one, if you have two, if you have all of them, if they're continuous, that's when you use multiple regression. So when you have one continuous and one categorical predictor, you still use multiple regression. When you have all continuous predictors, you still use multiple regression. Here's our example. It's basically a take off our previous example. Our dependent variable equals happiness. Our independent variable equals wealth. Our love oneself manipulation is a new thing. So it's just like, I'm going to make this up right now. Half my participants were asked to just write about why they like their favorite food. And then the other half were asked to write about why they love themselves. Or, you know what, we can even say, why do they like their favorite actor versus why do they love themselves? You can even say why do they love their favorite actor versus why do they love themselves. But I want to look at love oneself versus not love oneself. Okay? So here's our data. Hey, data collection got shut down because of COVID. So, I only got 6 participants. I thought y'all would find that funny. But look, I got a continuous dependent variable. We always have a continuous dependent variable. I have one continuous predictor, right? That's wealth, 1, 2, 2, 3, 1. That's just a wealth score, how wealthy they are on a 1 to 5 scale. People weren't that wealthy in my study, but I didn't collect that many. And then my love manipulation is categorical. So let's analyze that data together. All right, so we're now going to try to run a ANOVA with a continuous predictor without median splitting it, right? So we're going to run an ANOVA. We're going to get ANOVA type outputs. And what you can see is I've entered the data in from our example. So we got our dependent variables happiness. Our independent variable 1 is love. And our independent variable 2 is wealth. And independent variable 1, no, it wasn't love. It was, let me just look back here. Oh, it's a love oneself manipulation. So it's like 8 reasons why you love yourself or 8 reasons why you love your favorite actor. I don't know. I just kind of make some of this stuff up to kind of make the data analysis easier. But ultimately, we got this love oneself, love the other, love oneself, got 8 reasons why you love this other person, 8 reasons why you love yourself. And then your wealth measure on a 1 to 5 scale. Are you in the 1%? You in upper middle class, like stuff like that. Participant ID, that's important that is important if you have a within subjects design. Your next thing that's important is labeling your 2 independent variables. After that, you got to tell me if each independent variable is within or between. Now, ultimately, independent variable 2 will never be within, but, it's just kind of in there. And just if it does work out that way, it shouldn't be within because it's a continuous measure. Your independent variable 2 should always be that continuous measure. But, I like consistency. So is independent variable 1, is that within? Is it between, right? This will generally be no, but this will be whatever your variable is. Here we can see based on our participant, right? Other, self. We have 6 participants, 6 observations, so that's completely between there. We don't have to worry about that. But once we enter in our data and we click the run button, what we end up with is a very similar outputs to what we've had before. This is a note for Dr. Duricki. Right here is your ANOVA table, and you'll look, you have your self-love main effect, you have your main effect of wealth, which was a continuous predictor. This was your manipulated predictor. You have your interaction between the manipulated predictor and continuous predictor, and you have your error term. You have those lovely bars that let you see how big the effect is. You have your degrees of freedom, okay? And then you have your variance scores. You have your F statistics, your 95% confidence intervals of your F statistics. And if you notice, those 95% confidence intervals of your Fs are not perfectly balanced. And that's just because that distribution that's behind that statistic is elephant shaped, right? It's got that tail on that one side. And so it's never, when we find these 95% confidence intervals, we're not going to find a perfect symmetrical interval because we're not estimating a perfectly symmetrical distribution. So don't let those freak you out. These are just kind of like there. Eventually I'd like to have everything but that one disappear, but that's just kind of like, it doesn't have a confidence interval or anything like that. I wanted to show that the error divided by error is 1. I don't know why. I just wanted you to see that because that's important. So those are our F statistics. Then we have p-values for each of our effects. In this case, we do have a significant effect of our manipulation. And our confidence interval of that makes me not too scared about this effect. Worst case scenario, it's almost significant, right? Best case scenario, it is. And these p-values are tagged with these Fs, essentially. So they're also not symmetrically distributed. And that's just the nature of the F statistic here. But this allows you to check your estimate of that p-value. And then finally, your partial eta squared, where it has a very similar relationship. It's not symmetrical, the same stuff. But like for this effect right here, 95% of the variation in the stats that are relevant to this specific main effect, and that's this plus this. 95% of the total variation in error plus the effect is driven by our signal. So it's signal plus error, right? Signal over signal plus error. So 95% of that is predicted by independent variable 1 or self-love. 84% of the dependent variable is being predicted by wealth and error, and you can see that's a lot less. And you're like, hey, wait, what about, you don't want to penalize one main effect for another main effect doing well, so you separate them out. That's why it's partial eta squared. And then you got 81% here, right? But if you look at our confidence intervals, they range from 0 to 90% and 0 to 88%. The reason why they range to 0 is because they very well could be 0 in another situation. If you look, these p-values right here are 1 and 1. You know, these lower limits are 0 and 0. And so they're related to each other. They're not necessarily paired up perfectly because a lower limit on a p-value is the upper limit on an F statistic. Things like that. But ultimately, it works exactly like the ANOVAs I taught you before. Okay. We have another predicted graph. You saw the one earlier in the full multiple regression. This one's doing the same thing, except for, look, independent variable 1 is that categorical variable, that love manipulation for the other, that love manipulation for the self. And then it's when independent variable 2, which is wealth, is low and high. So when independent variable 2 is low, right, what do you see here? Well, you see a slight increase in happiness as a function of focusing on that self-love manipulation. But when wealth is high, you see a drastic increase by engaging in that self-love situation. So the self-love thing does increase happiness, but only when you're already rich. Probably due to some of the various... You know what? I'm not going to tell you why. I made up the data. You can come up with a reasoning. This right here, like, it doesn't matter for this situation because our other versus self only has 2 conditions, but it in fact does have a t-test associated with it, does have a p-value associated with it, does have a 95% confidence interval of that p-value, and has a Cohen's d associated with it. And so that's really interesting as well. That's just a follow-up to that specific test, right? And then you have just the continuous predictor. So this is wealth, the relationship between wealth on your dependent variable of happiness. You can see, like, we're looking for that specific, that relationship is a correlation coefficient. So that relationship's 95% confidence interval here, we're able to see it, but it's not written down for us, and I'm okay with that. But what you can imagine is turning that distribution right at the middle, right there at the axis of the graph, and you can see that the slope of this line, you can turn it all the way up so that this point goes up here and this point goes down here. So when the worst case scenario, it's a negative relationship, you turn it the other way, where you crack this all the way up to its 95% confidence interval and this all the way down. And then you're also, that best case scenario is a very positive relationship. 0's included in there, so we know the 95% confidence interval includes 0. Because we're just playing around with multiple regression, you know, you don't really need anything more than this for your continuous variables. You don't need anything. Oh, okay. So I'm going to click reconnect. But so what we have is we have our ANOVA table that we're familiar with. Interpret it just like all the other ones. We have our follow-up to a significant interaction, but it's nice to look at this. We have our follow-up to a significant main effect on our categorical predictor. Now, we wouldn't run this follow-up because there's only 2 conditions, so we know where we don't need to figure out where the difference lies, right? Like in an ANOVA, because we know that the 2 conditions would be different if their p-value is less than 0.05, which in this case it actually is, and that is something that we already found. And then this right here is our follow-up for a significant main effect on our continuous predictor. It has no numbers associated with it. It's just a picture. You don't have to include it. You just can describe it if you want. I put it in there just for visual reference. It's not really important. What is important, I think, is this right here, your ANOVA table. That's the most important. And then your predicted values, just to let everybody see what happened. Everything after that is just kind of like me trying to be consistent. So for your homework, you know, feel free to use some shortcuts. But if you don't understand this, I need you to get on the horn. I need you to talk to me on Monday or Wednesday, and I need us to make sure you know what's going on. You will never even think about using a median split again. That is the takeaway from here. And you will do the correct analysis. What I want you to know is that multiple regression, which I've only given you a little bit of, I could teach a whole class on it, okay? It's replacing ANOVA, it's basically replacing ANOVA in grad schools, even though people still run ANOVAs. They're starting to move away from that even because it's just better data analysis skills. So if you plan to go to grad school, welcome to the world of multiple regression and welcome to that sort of stuff. If any of you are in grad school and need help with your grad stats homework, I would love to help you all out with some grad stats homework. I've had some other students take me up on that, and just seeing what they're teaching now makes me wish I could go to grad school now instead of when I did. The stuff that they're teaching y'all is so much advanced. I don't want you to worry about this at all. I want you to know this exists, and you know where I am. So if you ever need help with an analysis like this, I'll help you out. And I just want that to be clear. Like, this stuff is going to take more than one silly lecture to understand it. I hope it makes sense, but I've given you like a quick overview. I haven't even really given you a foundation, all the foundational principles, you know. I've told you there's an equation beneath this. We're predicting betas, but ultimately there's a lot more to learn. And so I just want you to be prepared for what should be coming next in your statistical life. All right, your homework is pretty fun. So you're either going to measure 3 continuous measures from 5 people you know and run a multiple regression on it, or you're going to redo your analysis if you used a median split to analyze your data. I know this is Hannah. I believe it's Olivia too. Anybody that did a median split on their data, I want you to rerun your analysis just so you know what you found. Both groups, just give me a quick summary of what you found. You know, both are, you know, it doesn't have to be too detailed, but just give me that quick summary of what you found and the summary of your statistics. So both groups will have 2 main effects in an interaction. Just the group on the left will have it for continuous variables, and the group on the right will have it for both continuous and categorical variables.